Review of sections 1.4 through 1.6 for the 1.4 through 1.6 quiz. So in problem 1, we have a graph, and first we need to graph y equals f of x minus 1 based on the graph of f of x, which is the original graph that is given to you. So if we want to graph y equals f of x minus 1, since the minus 1 is in the back, we know that we want to move all of the coordinates down by 1. So all of the y values will reduce by 1. So our new graph will be at negative 2, comma 2, at 0, 1, at 1, negative 1, and at 4, negative 3. So that is our graph for A. For B, we want to graph y equals f of x plus 2. So now since the plus 2 is inside with the x, we know that it's going to shift 2 towards the negative side, or 2 to the left. So if our original point was at negative 2, comma 3, it's going to be at negative 2, comma 5. And our other point is at 0, 2, so it's going to be at negative 2, comma 2. Other point is at 1, comma 0, so it's going to be at negative 1, comma 0. And our last point is at 4, negative 2, so it's going to be at 2, negative 2. So that's our graph for B. For C, we have y equals f of negative x. Since the negative is inside with the x, we're going to have a reflection, but it's going to be a reflection over the y-axis. And the reason for that is all of our x values that were negative are going to now become positive, and all of the x values that were positive are now going to become negative. So I'm going to make a separate graph so we can see this a little bit better for C. So we'll have our first coordinate used to be at negative 2, comma 3, so now it's going to be at positive 2, comma 3. Our next coordinate used to be at 0, comma 2, and it's actually going to stay there because if I multiply 0 by negative, it just stays 0. Our next point was at 1, comma 0, so it's going to be at negative 1, comma 0. And our last point was at 4, negative 2, so now it will be at negative 4, negative 2. So our graph is reflected over the y-axis. For D, we have y equals negative 2 times f of x. Since the negative 2 is on the outside, it's going to be a vertical stretch, and it's also going to be a reflection over the x-axis. Basically, if we just take all of our y values of our original points and multiply them by a negative 2, we'll have our graph. So if I used to have a point at negative 2, comma 3, it's going to be at negative 2, comma negative 6. Way down there. If I used to have a point at 0, comma 2, it's going to be at 0, negative 4. If I used to have a point at 1, comma 0, it's actually going to stay at 1, comma 0. And if I had a point at 4, negative 2, it's going to become 4, positive 4. For our last one, y equals the absolute value of x. Since the absolute value of f of x, since the absolute value bars are around f of x, it's going to make all of our y values positive. So if we look at the original function, we have negative 2 comma 3, that has a positive y value, so it's going to stay. The same thing with 0, 2, and 1 comma 0. The point that's going to change is the point that used to be at 4, negative 2 is going to now be at 4, comma, positive 2. Let me use a different color so the graph looks different. So the graph is actually going to have all the same points, except this last point is going to flip up like that. And that would be the absolute value of f of x. For number 2, part A, we want to find f minus h of x, which is the same as f of x minus h of x. So if f of x is 3 minus 2x, I'm going to subtract h of x, which is 3x squared plus 2. And when I subtract it, I want to be careful to distribute the negative and combine like terms. So my final answer will be negative 3x squared minus 2x minus 5. For B, I want to find g of 1 minus h of 1. So first I can find g of 1, which would just be the square root of 1, and h of 1, which will be 3 times 1 squared plus 2. So I have 1 minus 5, which equals negative 4. For C, we have h of x divided by g of x, so that would just be 3x squared plus 2 over the square root of x. And you do not need to rationalize this function. You can just leave it as is. There's no other way to simplify it. For D, we want to find f times h of negative 2, or f of negative 2 times h of negative 2. We could do this a different way than we did B. We could actually find the equation first and then plug in negative 2. So if we find, actually it would be easier just to find f of negative 2 and then h of negative 2 and multiply it together. So f of negative 2 would be 3 minus 2 times negative 2. And we want to multiply that by 3 times negative 2 squared plus 2. So that would give us a 7 times 14, which is 98. For g of f of negative 2, sometimes it's easier to rewrite it as g of f of negative 2. This tells us that we first want to find f of negative 2, which would be 7. Then we want to find g of 7, which is just the square root of 7. For h of g of x, we actually need to take g of x and plug it into h of x. So g of x is the square root of x, and that is going to go in for the x in h of x. The squared stays there and the plus 2. And then we can simplify it. The square root of x squared is x. So our final answer is 3x plus 2. For the last question, what is the domain of C? First, let's look at what the problem was for C. We see that we have a square root in the denominator. So if we wanted to plug in numbers for h over g of x, we know that we would not be able to plug in a 0 because we can't divide by 0. And we know that we can't plug any negative numbers in for x because you can't take the square root of a negative. So our domain would be from 0 with a parenthesis, since we can't plug it in, to infinity. And remember, infinity always gets a parenthesis. For number 3, if f of x has a domain between negative 3 and 2, and g of x has a domain between negative 2 and 4, find the following domains. Well, we know that if we take two functions and combine them in any way, adding, subtracting, multiplying, or dividing, the domain of the combination function is the domain of the intersection of the two functions. So, if we have one domain between negative 3 and 2, and another domain between negative 2 and 4, we can see that the domains overlap between negative 2 and 2. So that would be the domain of my combination function. Part B is a little bit different because we're just dealing with f of x. So if we have f of x plus 1, you can kind of think about the graph shifting. It used to be between negative 3 and 2, and if we add 1 to if we do x plus 1, we know our graph is going to shift 1 to the right. So then our domain will be in between negative 4 and 1 instead of negative 3 and 2. For number 4, in order to show that two functions are inverses of each other, we must first show that f of g of x equals 1. So, equals x. So, first we'll find f of g of x. So we'll take g of x and put it inside f of x. So f of g of x equals the square root of x squared minus 1 plus 1, which equals the square root of x squared, which equals x. We also need to show that g of f of x equals x. We have to show both things. So, for g of f of x, we'll take f of x and plug it into g of x. So we'll get the square root of x squared plus 1 squared minus 1. I'm sorry, it's just x plus 1. Let me erase the squared. There we go. All right, so when we square that, we're going to get x plus 1 minus 1, which just equals x. So we proved that the two functions are inverses of each other. In problem 5, we want to find the inverse of the function f of x equals the square root of 9 minus x. So first we want to think of f of x like a y, and then to find the inverse, we want to switch x and y. So we have x equals the square root of 9 minus y. So we're not done yet. We want to get the y by itself. So we have our inverse function equation. So I'm going to square both sides. So I have x squared equals 9 minus y. And then I'm going to add y to the other side. And then subtract x. So I get y equals 9 minus x squared. For the restrictions on f inverse, we know that the domain of our original function is negative infinity to 9, since we can't take the square root of a negative, and the range is 0 to infinity, since it's a square root. When we find the inverse of a function, the domain and the range flip-flop. So the domain of our inverse function will be from 0 to infinity. And its range, even though it didn't ask, we can still say it's between negative infinity and 9. And 9 should have a bracket since we can plug it in.